See, in the third class of this nuclear physics, we have to study these four factors. What is ionization, specific ionization, range of alpha particle, and finally Geiger-Nuttall law. You know that from the radioactive element, alpha particle is emitted. Assume that this is an alpha particle. Initially, it has got certain kinetic energy which is known as maximum kinetic energy. And in its path, alpha particle came across an atom which is present in the air medium, and it knocks off an electron from the orbit of this atom. That means it removes an electron, and this becomes positive ion. And this removed electron in motion settles with another atom, and this is called as negative ion. That means which atom which loses an electron is called as a positive ion. Atom which gains an electron is called as negative ion. So when an alpha particle hits an electron, it transfers its little bit of energy to an individual electron. That individual electron takes that energy and moves. Then alpha particle proceeds in the same direction, but with less energy compared to the point at A, because it has given to an electron. Then further it moves, same phenomena occurs again. It finds another atom, removes an electron, it may settle on another orbit. Then this is once again positive ion, and this is negative ion. This process continues. Then alpha particle loses that certain energy. Step by step, alpha particle loses the energy and producing ion, positive and negative ion. The process of removing or addition of an electron to an atom is called as ionization. Then ion pairs are produced. This is one pair and this is another pair. The number of ion pair produced per unit length is called as specific ionization. Number of ion pair produced per unit length is called specific ionization. Then what is the range of alpha particle? See, alpha particle starts with the maximum energy from this point. Then when it is traveling, ionization takes place. Step by step, this alpha particle loses an energy. Then stage reaches, though it hits an electron is not removed from the atom, because alpha particle carries very less energy now. Then the distance which the alpha particle travels such that it loses energy to the extent that it cannot further ionize. So it goes on losing energy step by step. At one stage, further it cannot ionize. The distance traveled by the alpha particle, so that in the air medium, so that it cannot further ionize because it loses an energy, that distance is called as range of the alpha particle. That range of the alpha particle is represented by R. Then the range of the alpha particle depends on what? So, first one, the range of the alpha particle depends on the energy, kinetic energy with which the alpha particle is emitted. So, natural, if it has got large kinetic energy, it travels longer distance. If it has got less kinetic energy, it travels smaller distance. Range depends on the initial energy or kinetic energy of the alpha particle. Then second one, the nature of this radioactive element, what type of radioactive, whether radon or thorium, it also depends. So the nature of the radioactive element. And the third one, the material through which this alpha particle is traveling. Assume that this may be solid, it may be liquid, it may be gas. Then when alpha particle enters the solid, it may travel a smaller distance in terms of millimeter. When it travels, this is solid and this is liquid, it travels little bit longer distance, again it is in millimeter. So when alpha particle travels in the air medium, it may traverse longer distance. When alpha particle enters the material medium, that material medium absorbs the alpha particles. That means the range is maximum in the air medium and it is minimum in solid and liquid. Then Geiger and Nuttall have measured the range of the alpha particle of different radioactive elements by measuring their velocity, and they gave the relation between the range of the alpha particle and also velocity as R is equal to A V is to 3, or in other words, this is range of the alpha particle is directly proportional to cube power of the velocity of the alpha particle, which is Geiger-Nuttall law. Or this is R is equal to some constant A into V raised to cube. Call this equation as 1, where A is constant of proportionality. The value of A is 9.6 into 10 raised to minus 24. Then this equation 1 gives the relation between the range and velocity of the alpha particle. And you know that the velocity and energy, kinetic energy, are related by E is equal to half mv square. That means energy is directly proportional to square of the velocity. From this relation, I can write another formula for range. R is equal to B into E raised to 3 by 2, where B is another constant. It is 3.18 into 10 raised to minus 3. So this is Nuttall law gives the relation between range and energy of the alpha particle. They have also derived the relation between lambda and R. What is lambda? Lambda is decay constant. So the Geiger-Nuttall law in another form is it is log lambda is equal to A plus B into log R. So call this equation as 3. Here A and B are constants. From this it is clear that as R increases, means if the range is maximum, decay constant is also maximum. What about half-life? Half-life of the radioactive element is minimum because you are writing this is lambda is equal to 0.693 divided by T. If T increases, lambda decreases, lambda increases, T decreases. And they have plotted using equation 3 this graph as log R versus log lambda for different series of radioactive element. What do you mean by different series of radioactive element? Means assume that this is radon radioactive element. It emits alpha or beta or gamma radiation. It changes into another element because mass number and atomic number changes. If this is still a radioactive element, it once again emits the alpha, beta, gamma radiation. This process continues. It is called as radioactive series. So for radon, they got the straight line. For thorium also they got the straight line. Like that, for different radioactive element, the straight line is obtained by taking log R versus log lambda, and the slope of this straight line gives this B. So it is constant for all radioactive element. So also you know that R is directly proportional to E. Here range is directly proportional to energy. They got another relation between this decay constant. This is log lambda is equal to C plus D into log E. All this equation as 4. So all these 4 equations gives relation between V and R, relation between E and R, relation between lambda and R, and relation between lambda and E. So this is regarding Geiger-Nuttall law. Now let us solve some examples. I hope you are having the notes with you. See that 8th question. What is the range of 5 mega electron volt alpha particle? So they have asked what is R. 5 mega electron volts means they have given energy. This is 5 MeV. You convert this into joules, it is 5 into 10 raised to 6 mega 1.6 into 10 raised to minus 19 joules, and V is given 3.18 into 10 raised to minus 3. Now your range is B, because energy is given is to 3 by 2. You write this as B into E into square root of E. Then if you simplify this E, your B is 3.18 into 10 raised to minus 3. So 5 into 1.6 is 8. 10 raised to minus 13. And into square root of 8 into 10 raised to minus 13. If you simplify this, you are going to get this as 2.27 into 10 raised to minus 21 meter. Then see the next one, 9th. Neptunium 237. That means they have given it as 93 N P 237 emits an alpha particle of energy. That means E alpha is given. This E alpha is 4.19 mega electron volts. Calculate alpha disintegration energy. Q is what? You know your Q is K E alpha into A upon A minus 4. Here kinetic energy of the alpha particle is 4.19. Your A is 237, then 237 minus 4. If you simplify this, you are going to get it as 4.26 MeV. Then see the 10th one. (212Bi). Releases 6 group of alpha particles, 6 groups. In one case, it releases alpha particle of energy. In one case, Ke alpha 6.09 MeV, and decays in ground state of 208 Bi. TL, sorry, 208, it is TL. Calculate corresponding disintegration, and once again Q. You know this Ke alpha into, once again you have to use this formula, A upon A minus 4. See, they have given here the sixth group of alpha particle. If 6 times the kinetic energy of the alpha particle is given, you are supposed to calculate 6 times this equation. Now only one kinetic energy is given, it is Ke alpha 6.09 mega electron volts. Then you have to substitute here, it is 6.09 mega electron volts. A is 212 upon 212 minus 4. You simplify this. Then 11th. Polonium 210. Emits alpha particle of energy 8.776 MeV. Ke alpha 8.776 MeV. Calculate the corresponding disintegration energy. Once again, Q is what? The same formula you have to use this. See, in 5 marks, first example. Calculate the alpha particle potential barrier in case of 84 PO 212 alpha particle potential barrier. Now, this is, you know that this alpha particle potential is 1 upon 4 pi epsilon naught into z minus 2 into 2 e square divided by Rn, or this is 1 upon 4 pi epsilon naught into, here z is 84 minus 2 into 2 into 1.6 into 10 raised to minus 19 whole square, that divided by Rn is R naught into A raised to 1 by 3. Then, so I hope you will substitute the value of 1 upon 4 pi epsilon is 9 into 10 raised to 9, 82 into 2 into 1.6 into 10 raised to minus 19 whole square. R, what is the value of R naught? I have told in the theory, 1.2 into 10 raised to minus 15, and A is, what is it, 10 raised to minus 15 or what it is? Yes, 10 raised to minus 15. Your A is here 212 raised to 1 by 3. So many volts you will going to get. You simplify yourself. So simplify that potential barrier is so many volts. I think this completes your first chapter of nuclear physics.